understood that equations of continuum mechanics can be written in a special form it comes from physics. These equations are earlier Lagrange equations for a functional which is called Hamilton action, and we have to write these earlier Lagrange equations under some constraints: conservation of the mass, conservation of the entropy, and other constraints. So they are earlier Lagrange equations for a constrained Lagrangian. Okay, so this structure is very nice. It comes from physics. But what is important is the following question. It is a mathematical question. Your equations should be well posed. So this additional assumption or hypothesis to verify the equations, or maybe I will write like this: the Cauchy problem for these equations should be well posed. What is the meaning of this word, well posed? Indeed, it depends on the equation of state, it depends also on physics, but what is the meaning of this word, well posed? So, it was introduced by Adamar, Jacques Adamar, and it means three things. First of all, you should have uniqueness of the existence, first of all, of the solution. Second, uniqueness of the solution. And finally, continuous dependence on initial data. Okay, we understand more or less what does mean existence. We understand more or less uniqueness. It depends on spaces where you consider solutions. But what does it mean continuous dependence on initial data? Let us show you this example proposed by Adamar. Consider just Laplace equation utt plus uxx for some variable u and the following initial data. U as t is equal to 0 is equal 1 over n squared cosine n x, and second derivative ut when t is equal to 0 is 1 over n cosine n x. And we can find the solution of this problem. Solution is given in explicit form. So just u is equal 1 over n squared exponential nt cosine of nx. Indeed, let us check. If I put, first of all, let us show this solution. So I differentiate with respect to t, I obtain exponential n squared exponential nt cosine nx, and I have to differentiate cosine 2 times. First time I obtain n sine with sine minus, and after that cosine, so the same n squared exponential nt cosine nx. So it is 0, the solution. And If t is equal to 0, I obtain that. If I differentiate with respect to t, I obtain that. So it's okay. But what happens if I consider the case when n goes to infinity? We see that the norm of initial data u goes to 0 when n goes to infinity. However, the solution u for any time t goes to plus infinity when n goes to plus infinity. So this solution will appear from nothing, from 0. This is what is called Adamar case, Adamar example, where there's no continuous dependence on initial data. Now, how to formulate this property in mathematical way? For example, is it possible to propose a mathematical system governing equations for which the Cauchy problem is well posed? And this class of equations was proposed in 50s by Friedrichs. In particular, he proposed to consider what he called symmetric T-hyperbolic systems of equations. In one case, these equations are in the following form. I consider u the vector of unknowns, ut, A is some matrix, not necessarily constant matrix, plus b ux is equal to 0, where A is a symmetric matrix, which is positive definite, and B is just a symmetric matrix. So of course I can add additional space variables, but just to simplify the things, I will consider the case of one space variable. And this system is called symmetric T-hyperbolic in the sense of Friedrichs. Okay, symmetric is clear because we have symmetric matrices. Why T-hyperbolic? The classical definition of hyperbolicity is the following. System 1, okay, general system, ut plus cux definition is equal to 0 is hyperbolic if two conditions are satisfied. First one, eigenvalues of C are real, and second, the eigenvectors of C form a basis of Rn. Okay. And we can see that if we have the case of symmetric T-hyperbolic systems, they are obviously hyperbolic, because if I consider eigenvalues of the matrix B minus lambda E determinant, you obtain the polynomial. One gives us determinant of B minus lambda A is equal to 0, and obviously the eigenvalues are real, and the number of eigenvectors corresponds is exactly the same as the dimension of the space of unknowns. And also, when your equations are in such a form, one can prove that the Cauchy problem is well posed. So we have existence uniqueness of the solution, and also continuous dependence on initial data. Now the question is, if we have our equations of continuum mechanics, how to prove that our equations are such that the corresponding Cauchy problem is well posed. For example, if you have just hyperbolic equations, is it possible to rewrite them in such a form? The answer is yes, in 1D case. I will show how to do that. So, first case, if I will put here 2, if 2 is hyperbolic, then it can be written in the form 1. Okay, so let me consider the system ut plus cux is equal to 0. So I know, I will suppose in this case that C, okay, to be hyperbolic means that C can be diagonalized in a sense. Okay, so there exists a matrix T such that C is equal T diagonal matrix lambda T minus 1, because our system is hyperbolic. So you have the system ut plus T lambda T minus 1 ux is equal to 0. Now let us multiply the system by T minus 1 at the left. So I will obtain T minus 1 ut plus lambda T minus 1 ux is equal to 0. And finally, I will multiply this hyperbolic system by T minus 1 transposed. So we see that this matrix, I call it A, is positive definite. A is equal A transposed, it is obvious, is positive definite. And when I multiply by T minus 1 T minus 1 transposed, this matrix is symmetric. So this is B, and B is symmetric. So if the equations are hyperbolic, they can be symmetrized, so the Cauchy problem is well posed for these equations. Also, a very important fact is that our equations are written in conservative form, and this conservative form is just physical conservation laws. Conservation of the mass, conservation of the momentum, conservation of the energy, entropy if you want, for reversible process. And this helps also to prove that the system of balance laws can be written in the form of Friedrichs. And this was proved by 3 persons: Friedrichs, Lux, Godunov. Godunov was approximately 21 years old at this time. He proved the theorem, and it was repeated 10 years after by Lux and Friedrichs without citing Godunov. Okay, so what is this theorem? Let us consider a system of conservation laws ut plus f of u x is equal to 0. U is a vector of Rn, and f is a function from Rn to Rn. Smooth function. So, for example, for earlier equations of compressible fluids, you have in 1D case, for example, you have first equation, conservation of the mass, written in such a form, conservation of the momentum, rho u t plus rho u squared plus p x is equal to 0. And for example, I can take conservation of the energy or conservation of the entropy. If I take conservation of the entropy, I can write our system in the following form: rho s u x is equal to 0. For example, I can take 3 conservation laws in such a form, earlier equations of compressible fluids. Yes?
U is in Rn, but x is one-dimensional or?
One-dimensional. Indeed, I can prove that in multi-dimensional case, but it takes just more place. That's all. Exactly the same result. Now, suppose I will put here 3, that 3 admits an additional conservation law in the form E of u t plus g of u x is equal to 0, where E of u is a convex function of u. So, in particular, the Hessian matrix of E2 primes of u, is just the Hessian matrix dE over du1 squared and so on, is positive definite. Then the system 3 can be written in the form 1, so it can be symmetrized. So the Cauchy problem is well posed. So automatically, if you have a system of conservation laws, you don't need to check the hyperbolicity, because it can be symmetrized, and this property is automatic. So how to prove that? First of all, let us see what are consequences of the fact that you have an additional conservation law, E of u t plus g of u x is equal to 0. So let us derive that with respect to time. So we have gradient of E, gradient with respect to u, multiplied by ut plus gradient of g with respect to u multiplied by ux is equal to 0. But u verifies also the equation ut plus f of ux is equal to 0. So ut plus Jacobian matrix df over du ux is equal to 0. So ut can be replaced ut is just minus df over du ux. And I can replace ut in this equation. So you have gradient u e minus. So normally you have to consider that like a line vector multiplied by the column vector, and I transpose that. I'll obtain here df over du transposed multiplied by gradient of e minus gradient of g, all this stuff multiplied by ux is equal to 0 for any ux. So this one is 0. So there is some compatibility condition in terms of e and g. So this compatibility condition is finally df over du transposed multiplied by the gradient with respect to u of e is equal to gradient of ug. Compatibility condition in terms of e and g. Now what to do? How to prove the symmetrization of this system? Let me recall you some properties of convex functions. Okay, suppose you have a convex function e of u. I will consider new variables v, which is just gradient of e with respect to u. Indeed, because e is a convex function, you can find u as a function of phi and vice versa. This is just the theorem of implicit functions. Consider now Legendre transform of e star as a function of v defined by the following formula. It's scalar product vu minus e of u. So this function is considered as a function of v. Legendre transform of e of u. And we know very well properties of the Legendre transform. We can prove that if I take the gradient of e star of v, but gradient with respect to v, I will obtain u. Why? Just let me derive that. I derive with respect to v, so I obtain v, so u plus du over dv transposed multiplied by v, because I suppose that u is a function of v, minus derivative with respect to v is just gradient of e with respect to u, and here du over dv transposed. But this is v, so this one disappears. I will obtain u. Okay. Let me define also function g star of v. G star of v is just the following function. It is v multiplied by f of u minus g of u. And I will calculate the gradient of G star of V with respect to V. So the first term will be f of u plus df over du transposed multiplied by v. Indeed, all the time I use the following thing. If you have gradient of the product A, B, okay, it's just dA over dx, for example, gradient with respect to x, transposed B plus dB over dx transposed A. So transposed is very important. And I use all the time this simple formula. Okay, so two first terms minus. And when I take gradient of G, I will obtain du over dv transposed gradient with respect to u of G. Now, I have some compatibility condition. It is written here. So df over du transpose gradient of E is gradient of G.
What if you get a du over d transpose?
In the second term, okay. So normally I should have gradient with respect to V of G. So it is, I will write like this. dg over dv is equal du, sorry. F? This one?
Yeah.
Okay, you see this is scalar product. I use that.
But there's still a dependence of u with respect to v. So when you differentiate d of f of u with respect to v, you should get a du dv transpose df du transpose v. No?
No, because F depends on U.
And u depends on
Of course, sorry. Of course. So du over dv multiplied by v transposed. Yes. Thank you very much. Because it is equal f of u plus, and now it will be du over dv transposed df over du transposed v minus, okay, minus gradient of u g. And this is exactly compatibility condition, I think, because v is gradient of u e. So this term is 0. Thank you. If not, it doesn't work. So finally, we have obtained the following thing. So our system of conservation laws, ut plus f of ux is equal to 0, is equivalent, by using these new variables, to the system dE over dV. Okay, we'll write like this, or gradient, just gradient with respect to V, E star of V, derivative with respect to time, plus here gradient of G star of V, gradient with respect to V, x is equal to 0. Now I develop this derivative, and I will see that it will appear here symmetric matrix. So because the derivative with respect to t will be just second derivative E star with respect to v, so it's Hessian matrix multiplied by vt plus second derivative of g star with respect to v multiplied by vx. And now the property of Legendre transform, this matrix is positive definite. It is symmetric, of course, because it is Hessian matrix, and this matrix is just symmetric. B is equal bt. So we transformed our system of conservation laws to symmetric form, so we are sure now that the Cauchy problem is well posed for our equations if there exists a convex energy conservation law. Okay? Now, for our case, for example, the case of Euler equations of compressible fluids, an additional conservation law is just conservation of the energy. Conservation of the energy. So we have energy conservation law, Euler equations of compressible fluids. Rho epsilon plus 1 over 2 u squared t plus rho u epsilon plus 1 over 2 u squared plus p u x is equal to 0. Energy conservation law. So this is E and this is G. So the only thing to check is that this function E, which is rho epsilon plus rho u squared over 2, is a convex function of conservative variables. Of rho u and rho eta. It is entropy. So we have to replace arguments here to rewrite like this. It is epsilon of rho. We had here eta, so it will be rho eta divided by eta plus rho u squared divided by 2 rho. This energy. So exercise to check, to find the condition where this function will be a convex function of rho u, and rho eta. And the answer is the following. I will give the answer nevertheless. So if epsilon as a function of tau and eta, where tau is 1 over rho, is convex function of these variables tau and eta, then E will be convex. So convex function of rho u, and rho eta. In particular, it means that when you have Euler equations of compressible fluids, and your equation of state is van der Waals type equation of state, the Cauchy problem is not well posed. When you have polytropic gas, the Cauchy problem is well posed. Okay?
When you talk about additional conservation law,
Yes.
it's because it's not an Euler-Lagrange equation of the problem.
Indeed, this theorem has nothing to do with Euler-Lagrange equations. It's just abstract theorem proved by mathematicians, well-known mathematicians. Okay, just about general system of conservation laws. I explained at the beginning that we have, first of all, a nice structure of governing equations coming from physics. But it's not sufficient. We need something more, well-posedness of corresponding Cauchy problem. And by chance, not by chance indeed, additional conservation law, it's, for example, for this system energy conservation law, it is a consequence of the Noether theorem indeed, a consequence of the fact that our system are Euler-Lagrange equations for Hamilton action. However, the physical properties to add is the convexity of the energy. Okay, and the convexity of the energy is also some physical fact, and there is correspondence between this physical fact, convexity of the energy, and well-posedness of the corresponding Cauchy problem. So the logic is quite, it's not very complex, but not direct.
So if you look at the equation, it seems like you could also choose a variable, the energy, the
Exactly.
and the rho, and take the conservation of mass and the additional conservation.
It is possible, exactly.
Okay.
Yes.
But then you wouldn't have to assume that epsilon is convex. So you would
No, indeed it is equivalent in the sense that, so you can consider, for example, the density of, okay, what is important, the choice of variables indeed.
Yeah.
Okay, indeed you can mix conservation laws if you want. Okay, for example, you can consider, you have to play, so it's not direct. For example, good choice, rho t, rho u, rho eta, and after that energy. Okay, you can mix, for example, energy and say, okay, I will consider the entropy conservation law as a consequence of rho u, and equation for the energy. Why not? So you can formulate also a sufficient condition of hyperbolicity, convexity of the entropy. But it is equivalent convexity of the entropy, but the function of, you have to indicate variables. And this is not arbitrary choice of these variables, because it is related with conjugate variables v you have found when you considered energy as a consequence of these conservation laws. So this is why I didn't take indeed the entropy as additional conservation laws, because conjugate variables are very strange. But if you consider the energy like consequence of these equations, the conjugate variables are quite simple. This is the only reason. Okay. Okay. Now so I will discuss now how to obtain equations of multiphase flows by using the Hamilton principle. So we'll check hyperbolicity of these equations. We'll find symmetric forms of these equations, and also we'll discuss the following question: what is the sound speed in heterogeneous mixtures? So, for example, this is a very important thing, because how it is related with characteristic values. This is a very important thing because even now we can find in the literature the following discussion about sound speed in heterogeneous mixtures. So suppose you have heterogeneous mixture of the following form: one component, second component, first component, second component, and so on. Periodic system. And you consider sound wave propagating through this layered system. Let us suppose that the sound velocity is here c1, here c2, c1, c2, and so on. And you want to know what is the effective sound velocity in such a layered system. So even now, people, not all, but some of them, do the following thing. They say, okay, so I consider just some length L And mean velocity is just L divided by T. How to find T? So it's very simple. So T is equal. So first case, it's just, I will consider here L1, L2, L1, L2. So T is equal L1 divided by C1 plus L2 divided by C2 plus many times. Okay. So finally, C is equal L over T. So L divided by L1 C1 plus L2 C2. Okay, n times if you have some number of these periodic cells. So finally, this is formula. This formula is completely wrong. Okay, so I will explain how to obtain a good formula. Okay, multi-phase flows example of multi-phase flows are just soda beverages. Okay, typical soda beverage. So it's just bubbly fluid. Okay, liquid containing gas bubbles. So how to derive equations of multi-phase flows? Consider, for example, a volume omega, and in this volume you have several phases. For example, continuous phase will be denoted by 1 and dispersed phase by 2. Bubbles in a liquid. So we can say that omega is equal omega 1 plus omega 2. Omega 1 is the volume occupied by the continuous phase, and omega 2 is the volume occupied by the dispersed phase. Let us define a new quantity, which is called volume fraction, alpha 2. Roughly speaking, you have to pass to the limit. It's just the volume omega 2 divided by omega. So the same alpha 1 is omega 1 divided by omega. So it's just, we see that this quantity alpha 1, alpha 2, the sum is equal to 1. Sum is equal to 1. Now, first of all, I will obtain equations of conservative motions, so without dissipations. So I have to postulate the Lagrangian. Okay, let me consider Hamilton action. So integral from T0 T1 integral over omega L dt. So what is the Lagrangian? Lagrangian is the difference of the kinetic energy of the system minus potential energy. I suppose I can introduce some average values of field variables. So when I say the density of each phase, average density of each phase is rho A is equal 1, 2. So I will suppose that I average in this volume all, I consider it in this volume all the gas bubbles, and I deduced after that some average volume, average density of the gas phase in this big volume omega. So the same, I can introduce average velocity of each phase in this big volume omega, UA. And I can say, okay, so kinetic energy, if the velocities are not too different, for example, very often people consider the case when the velocities are very close to each other, u1 is equal to u2 is equal to u. In this case, the energy is just additive function of kinetic energies of each phase, so it's just the sum over A from 1 over 2 rho A u A squared over 2 multiplied by volume fractions of each phase. Okay, and when the velocities are approximately the same, you obtain here u squared over 2 alpha A rho A, the sum over A from 1 over 2, and this is just definition of the mean density. U squared over 2. This is rho by definition. Also, if you consider internal energy of the mixture, rho epsilon of the mixture W, energy of each phase. So it is alpha 1 rho 1 epsilon 1 plus alpha 2 rho 2 epsilon 2, and these functions epsilon A are functions of true densities rho A and entropies eta A. So this is the case of fluids. So finally, the Lagrangian can be written in the form rho u squared over 2 minus rho epsilon. And also we have some constraints to be respected, and these constraints are conservation of the mass of each phase. So conservation of the mass. So alpha A rho A T plus alpha A rho A U divergence is equal to 0. Conservation of the entropy of each phase. So d eta A over dt is equal to 0. Okay, that's all. So we have Lagrangian reduction these constraints, and we can reduce the machine I proposed before to obtain Gauss equations of classical continuity. Before we do that, okay, maybe also an example where multi-phase flows are very important, and this example comes from numerical treatment of interface problems. Imagine, for example, this classical public fluid system, for example. Imagine, for example, you consider the interface between two fluids or between solid and fluid. Typical problem appearing during solid fluid interaction. And you want to solve this problem numerically. What are you doing? Consider, for example, contains a mesh here. You know what to do when you are in the solid phase. Solid phase. So you can use here, for example, equations like this last time. Here, you can use other equations of compressible fluids. So in each cell, you know what to do. However, we can always find cells, mixture cells.
In each cell, both phases are present, solid phase and also fluid phase. What to do numerically? Because you have to say what is the value of the density in this cell, what is the value of the velocity in this cell, what is the equation of state in this cell. So if you say, okay, I don't care about that, all these clauses needed. So we need also to formulate governing equations of multi-phase flows even for this simple situation. Why is it necessary? Because indeed interface is moving, so you know the position of this interface. You cannot use classical boundary conditions between solid and fluid. Like if I say, okay, simple velocity of the fluid multiplied by the normal vector is equal to velocity of the solid multiplied by the normal vector. And also dynamic condition like sigma stress tensor of fluid multiplied by n is equal to stress tensor of solid multiplied by n. It's very difficult to use this condition because the position of interface is unknown. So we need also, even for this simple situation, derive multi-phase flow model. Before doing calculations, before showing equations of multi-phase flows, I will show some movies, and these movies were produced by using multi-phase equations. I will show how to derive them, and Nicolas Favry, who is present here, did these calculations. So, if we are capable, for example, to describe the following experiment, consider this experiment of a jelly cylinder folded down under the gravity. So that what it is completely elastic interaction and large deformations, not just hook law. So we need here to use here something which is different from classical hook law. So I can discuss the proposition we did, how we find the energy equation of state for the situation. But okay, what happens if it touches the ball and spreads until some limit size, and then squeezing and rebounding, complete rebounding, elastic rebound. And now this is calculations by using multi-phase flow model. So indeed, we calculated both the motion of air and also the formation of this solid jelly cylinder. However, because the velocity of impact is very small, just 1 meter per second, the motion of air is not very important. So we see more or less the same behavior as an experiment. Okay, some comparison with data. It's now much more interesting thing. So we have here the impact of a solid square, plain case, 10 by 10 centimeters, and it impacts this rectangle, 10 centimeters by 50 centimeters. All is in the air, so we have multi-phase flow indeed, and this is copper. And the impact velocity is 800 meters per second. Yes. And we used to describe this impact 3 types of models. First one is what we call elastic model. So we're supposed to have perfect fluid, perfect air, and the solid is pure elastic. What happens? We have motion oscillation of this solid, and also you see the picture of shock waves and reflection waves propagating in fluid. And this model is constructed by using this two-phase velocity. So what happens if you consider the same impact, 800 meters per second? However, it's not problem, it's just pure fluid. So a piece of fluid is impacting a piece of fluid, and the behavior is completely different. So we have immediately jet formation, filaments propagating to infinity indeed, and nice structure of shock waves, reflection waves inside of the fluid and in the air. So very often people model solids for large pressures as fluids, and we see it's nothing to do with it. You have enormous pressure to be sure that the solid behaves as a fluid. And also the first case is very strange because sure, elastic behavior is not acceptable for such velocities 800 meters per second. And finally, the last picture is the constructed multi-phase model where the solid was the elastic plastic solid. What happens here? At the beginning behaves like fluid, so you have small jet formation. But after that, the behavior is completely different. So you have appearing of cracks. So, and this solid will be decomposed into 3 parts. So it's much more real. Okay, this is just to explain the motivation why we need multi-phase flow models.
Now, how do the cracks will appear with shock continuity? Like you have different, etc. So cracks is appearance of new surfaces.
Okay, I will explain. So this is a very important question. It is for the situation I explained we need multi-phase flow model. So we need, if you know in our model we have no pure solid, we have no pure fluid. So we need to avoid the degeneracy of the model to very, very small quantity of gas bubbles inside of the solid. Indeed, to construct a good model, you have to include voids in the solid. Okay? But just to simplify situation, we include fluid inside of the solid. And then you have very strong reflection wave inside of the solid. The bubbles grow and it creates unique interfaces, creates cracks. In a sense, we have a criteria of cracking inside of solids due to this multi-phase flow.
So you have germs
Charms, yeah.
distributed more or less uniformly.
Yeah. Also, we have very, very small quantity of solid in the fluid, but indeed there's no influence. But the fact that you have fluid in the solid, it helps to have cracks. And it looks very nice. I mean, normally you should consider here 3 phases: fluid, voids, and solids. And it can be done, we did it, but to calculate numerically takes time. So maybe next year we'll show this picture. Okay. I will continue now the construction of the multi-phase flow models. I explain the motivation. Why I think this model. What is new with respect to classical continuum mechanics? New is the existence of this new variable volume fraction. So formally you should write the variation object Hamilton action, data T naught T1 integral object because it has the same velocity. We can consider the material volume here, rho u squared over 2 minus rho epsilon omega dt. So we have two types of variations. First one is the variation with respect to data x, and it was used the same machine I used before. And also there is a new variation with respect to alpha volume function. Alpha gas, for example, because alpha solid is related to alpha gas. Okay, the variation with respect to data is you give the equations of motion exactly the same way. So we have obtained rho u t plus divergence of rho u plus pi is equal to 0, but this expression p defined as alpha 1 p1 plus alpha p. The only definition is the definition of new pressure. And each pressure, pi, is expressed in terms of internal energies of each phase in the following form: rho pi squared and rho. And finally, how to obtain the equation spatial alpha change? It's just the Lagrangian. There's no dependence on derivatives of alpha, so we have to just find this derivative. But there's no dependence of alpha, which is not of spatial derivatives. Okay, let us continue there. So, what are unknowns in our system? With unknowns, mean density, rho, and I introduced alpha s, alpha gas, and also I will introduce what people call mass fractions. I gas, alpha gas, rho gas divided by the mean density rho, and also mass fraction of the solid or nothing. It's very strange. I used 1, 2 and solid gas, so I could write here 1, here 1, 1, because I consider just the case of two fluids. Okay? It was not the case of solid plus fluid. So y 1, 1, 1, and y2 are both rho divided by rho. They both mass fractions. And see that y1 plus y2 is equal to 1. And the equation for this quantity is very simple. Indeed, they like constants, in a sense. Because if you have two conservation laws, alpha 1, rho 1, t plus divergence alpha 1, rho 1, u is equal to 0, and conservation of the mass for the mixture is equal to rho t plus divergence rho u is equal to 0. Then, the consequence of that, the quantity y1 is conserved along trajectories. So it's sort of new entropy for our system. We have entropies of each phase conserving along trajectories, and this quantity is mass fraction conserving also trajectories. So finally, our Lagrangian F is rho u squared over 2 minus rho epsilon, and I have to write here the following. It's 1 divided by 1 rho, and add 1 and quadrant. So you see, normally this is a function of row 1 only, the density of the phase 1. And because the definition of y1 I divided by alpha 1 and multiplied by rho, so this is argument rho 1. And here y1, rho multiplied by y1 is just alpha 1, rho 1, this is the definition of the image. So I have to take this derivative, the edge over the alpha 1 by keeping constant y1, rho, and u. So I'll do that.
Excuse me. We have also an equation for with a derivative with respect to alpha 2.
Yes, but I have to replace, because they are related by algebraic relation,
Okay.
I don't
You
want
have it.
so I have to write here minus alpha 1, so this so I have y1 rho is epsilon 1 over rho 1, and after that derivative with respect to alpha 1, so I have y1 rho alpha 1 squared sine minus plus y2 epsilon 2 rho 2, and here y2 rho over computed alpha 2 squared. It's just the edge over alpha. Now, so I have g epsilon 1 over g rho 1 minus 1 squared rho divided by alpha 1 squared. So I give it by rho. The same security, the rho there plus g epsilon 2 over g rho 2 y squared plus j alpha squared. I just multiply by 0 by rho. And this is by definition rho 1 squared. Definition of mass fraction. And this is by definition rho 2 squared. By definition, rho 1 squared g epsilon 1 over g rho 1 is p1, phase 1. By definition, rho 2 squared g epsilon 1 over g epsilon 2 over g rho is p2. So this new equation coming from the variation of the volume fraction is just equality of pressures. The pressure, mean pressure in the phase 1 is equal to the pressure in phase 2. If you have dependence on derivatives of the volume fraction, it happens also. For example, bubbly fluids where you need to take into account bubble oscillations and so on. So much more complicated expression with it here. I have carried to show how it works. It's not very good. So finally, we have the whole system of Gavrilyuk equations describing one velocity multiplies each shape. And this is the quality system. So I'll write the system in one case. Rho t plus rho u x equal to 0. Conservation of the mass of the motion. Conservation of the moment. Rho u plus rho u squared plus p x equal to 0. Definition of the pressure. P is because P1 is equal to P2. P is equal to P1 is the same. Conservation of the entropy of each phase is equal to 1, 2. conservation of the mass fraction, for example, of the fraction y1, because y2 is just something with 1, okay, the system is closed. Because this is just an algebraic equation permitting us to find the volume fraction as a function of other variables. Let us check that the system is hyperbolic, and we will find some velocity of such a system, and we'll find finally what is the sound speed in heterogeneous mixture. And this sound speed has very, very strange properties, but these properties were verified experimentally. Okay. Let me first, I don't want to use this equation because I need to use implicit function theorem to justify that I can find y volume fraction as a function of other variables, calculate all the derivatives and so on, so it's too long. So simplest way is to do the following. I consider mass conservation law in the form rho x equal to 0. I divide by rho squared g rho over dt 1 rho squared plus 1 rho x equal to 0, and I introduce the volume fraction, not volume fraction, specific volume of the picture tau 1 over rho, and with this definition I obtain t tau over t minus tau ux is equal to 0. It's the first equation. Why this equation is important? Because the expression for specific volume tau is very simple indeed. If rho is alpha 1, rho 1 plus alpha 2, rho 2, then by dividing by the expression taking rho minus 1, I obtain tau is just y1, tau 1 plus y2, tau 2. It's completely pure. Why it is better? Because y1 behaves like a constant, conserves all projectiles. So now I will calculate this quantity t tau over dt. It is equal because y1 and y2 are constant on trajectories, so it should be just y1 t tau 1 over t plus y2 t tau 2 over dt. Now, because the expressions are the same, it's very simple indeed to find the derivative, because tau y is a function of pressure Pi and entropy. So just because pressure in the liquid, in the fluid, is a function of tau y as I, so I can eliminate find tau y as a function of Pi. So I will derive that p tau y over t is p tau y over t I. And here I can write just p without putting index I because expressions are the same. Plus t tau I over tsi over dt, but the entropy is conserved, so 0. And this, what is this?
Yes.
Sorry?
Yes.
Yes.
Yeah.
The entropy.
Sorry.
Because Peter used S for entropy. So now this quantity, when I replace now tau I by 1 over rho, it will be minus 1 over rho I squared, d rho I over d I. And this is inverse to the sound speed. By definition, sound speed in a fluid is just the derivative dpi over d rho I squared ci squared, just definition where eta I is closed. This is the definition of sound speed of fluid, classical fluids. So it will be minus 1 over rho y squared ci squared dp over dt. I can sum them. So obtain d tau over dt is equal minus 1 sum y I over rho I squared ci squared dp over dt sine minus. So it is equal to 1 sum I alpha I divided by rho I squared ci squared over dt equals sum I, so rho I rho I ci squared. Something wrong here because I divided by rho. And I will write this like minus 1 over rho cw squared dp over dt, where cw squared, that is 1 over rho cw squared, is by definition sum of I alpha I rho I squared. New quantity. So finally, it is equal just minus. So that W in wood. So it was first surface to calculate this velocity in the case of the mixture solid. They can think solid like a fluid. So now what happens with our system? Finally, our system is as follows. So the d tau over dt minus tau dt minus 1 over rho cw squared dp over dt minus tau x is equal to 0. And 1 over rho is tau. So we will like sine plus here and tau. And finally, I multiply by cw squared. Sorry. So it will be dp over dt plus rho cw squared ux is equal to 0. It's not just no. So there is how much? Yes?
Why the rho?
the dimension is good. Okay. Now, 1 over rho pressure. So I should write somewhere here rho because this dimension is not good. This dimension is 1 over rho derivative. Okay. The dimension of the pressure is just rho CW squared. So somewhere I have to write rho. 1 over rho. So it should be rho squared somewhere. Okay, but I don't see. I don't see
When we get to y,
yes. I'm by the dimension.
there was 1 over y.
Okay, exercise question. So sure, right, throw somewhere because okay, maybe okay. Okay, I don't see, but it should be a rho somewhere. So the first equation is dq t plus rho squared x. The second one by using the conservation of the mass unity of rho dq over t plus bx is equal to 0. So just divide the rho by writing 1 over rho. Also equations for the entropy that I with g is equal to 0, g y over g. So just let me write the matrix, calculate eigenvalues you will see, and next time I will have a discussion about that. So I consider unknowns u as beta I and yi 1, for example. Y2 is just operation. And I will write the system in the form g plus ax 0. So this matrix is a different matrix. So I can just calculate the matrix. A variables are eta 1, eta 2, y1. Because this is material derivative, we have dx divided by u. So this is u. Ux rho CW squared 0, 0, 0. Dx 1 over rho u 0, 0, 0. 0, 0, u 0, 0, 0. Now we get to the eigenvalues, and we will obtain, because the structure of this matrix is very simple, indeed, you obtain multiple eigenvalues, 3 eigenvalues, lambda is equal to u, lambda 1, 2, 3 is equal to u, and lambda 4 and 5 is determined only by this 2 by 2 matrix, and the answer is lambda 4, 5 is u plus minus CW. So CW is a true sound velocity in this system. one can prove that for these multiple eigenvalues, we have exactly 3 eigenvalues. So the equations are hyperbolic. It's a cheap property is what goes into this system. Hyperbolic. So I have just 1 minute to find the error. Okay, you found?
You can have the homework.
Show please.
We need it as a homework for you.
No, it was solved this problem. Yes. Okay. So this is okay. Okay. Now I should. This is not good. Yes. Okay. Sure, please. So because I can see
When you define a CW to square,
so I have to write here. Sorry. Yes. Yes. Yes.
you lose the dimensions of the qualities.
So it should be rho squared CW squared. So
Yeah, otherwise you lose the
yeah, okay, so it was correct. So finally this is the result and we will have discussion. Okay, maybe one comment is very deep. How to get this formula just from on figures without many calculations. So we say let us consider just the following situation. You have a beam with periodic structure as Sergei started. Say one piece of one material, then piece of another material, then piece of one material, piece of another material, etc. And say Young modulus of one material is E1, Young modulus of another material is E2, and so on. And you would like to find the Young modulus of the entire beam. What does it mean? Say you the Young modulus of of this effective structure when you neglect the microstructure. You apply here some displacement, say U, to this beam, and you measure the force, say, and you say that effective modulus is, and say if you apply some displacement, you can solve completely this problem because it is one-dimensional ordinary differential equation, and you find the force which you have to apply, and the coefficient which stands if this is the total length L, then and so this is effective, effective strain, and the coefficient that stands here is the effective modulus, right? And from this simple problem, you can find that the rule for the effective Young modulus of the entire system is 1 over E equal to, let's say for simplicity, this length R equals, so this would be 1/2 of 1 over E1 plus 1 over E2. And now we may recall that the relation between velocities and Young modulus, the velocities, say, velocity in the first continuum is square root of E1 divided by rho. Velocity in the second continuum is square root of E2 divided by rho.
And if you, here you solve the static problem. And when we consider the wave, we consider low frequency waves. So this is actually for low frequency waves, this beam reacts almost quasi-statically for low frequency. And therefore the effective frequency for this low frequency wave would be square root of E over rho for the entire structure. And if we plug these speeds in the equation for effective models, what do we get? 1 over rho c squared equal to 1/2. Again, we can put here different densities if we wish, but say that densities are the same. Then we have 1 over rho c1 squared plus 1 over rho c2 squared. Okay, that's okay.
This is exactly the proof by Wood. This is why it is called Wood sound speed. So because he made this proof for latest